In this video, we're going to prove a few properties of ring homomorphisms. In the previous video where we defined homomorphism, we talked a little bit about how if we know that there's a homomorphism between two rings, R and S, then we know that there are some structural similarities between the two that the map preserves. And in this video, we're going to flesh that out a little bit. So let's start with a basic property of homomorphisms. This will look very familiar from the work that we did with groups. So this we will call Theorem 1. If phi from R to S is a ring homomorphism, then phi of the zero element of R, that is phi of the additive identity of R, is equal to the additive identity of S. Now technically we already know this is the case because in order to be a ring homomorphism, phi has to be a homomorphism of additive groups first. And if we have an additive group homomorphism, then phi of the additive identity has to be the additive identity of S. But we'll prove this anyway just to illustrate how to use the properties of homomorphisms. So here's a proof. We're going to do this in a way that is probably familiar if you remember playing with group homomorphisms. We're going to make a clever play on the additive identity. We're going to use the fact that the additive identity plus itself is the additive identity. Okay, so this is something we know. And probably if I'm starting a proof with this, I should start with some words. We know this is true. There we go. I just feel like it's rude to start a sentence in a proof with a formula. Anyway, so we know that that's true. And then using the fact that phi preserves addition, we can say phi of 0r plus phi of 0r is equal to phi of 0r. And now we're in business because we know that we have additive inverses, so we can just add the additive inverse of phi of 0r to each side. And then we will get, sorry, this takes forever to write this down, and it's a little bit hypnotic because I'm writing down the same symbols 5 times. Anyway, on the left side we will get phi of 0r, and on the right side, because we have phi of 0r plus its own opposite, we just have, that's the additive identity of S, and that's the proof. Okay, now here's a fun fact though, because the next thing you might think is, well, if we can use the fact that phi preserves addition to prove that phi of 0 of R is equal to 0 of S, then certainly we ought to be able to use multiplication properties in the same way to prove that phi of 1 of R has to be 1 of S. But that's actually not necessarily the case. And it's not necessarily the case for kind of an annoying reason. So here's an example. I'm going to define a ring homomorphism from Z mod 10 to itself as follows. And I'm actually just going to define this using a table of values. So this is X, and then here's phi of X, and then here's the map. So I need outputs for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the outputs will be 0, 6, 2, 8, 4, 0, 6, 2, 8, and 4. And I will leave you to verify that this actually does give us a ring homomorphism. It actually, we know that it will define at least an additive homomorphism because all we're doing is we're taking every element of Z mod 10 and multiplying it by 6. This is really the map phi of X equals 6x for all x in Z mod 10. And now that I have a formula, I can actually use that to show that this will be a multiplicative homomorphism. You might try just using some of the values in the table to convince yourself, because in the previous video we saw a map that looked an awful lot like this and wasn't a homomorphism at all. It did not preserve multiplication. But here, if I take phi of xy, well, that's equal to 6xy. But if I take phi of x times phi of y, that is equal to 6x times 6y, and that's 36xy. But hey, this is Z mod 10. So that's really the same as 6xy, because 36 is congruent to 6 mod 10. So these really are the same. They're equivalent, and therefore this does preserve multiplication. It preserves addition. You can check that using the distributive property. So this is a ring homomorphism. But is phi of 1 equal to 1? No. Phi of 1 is equal to 6, which is not the multiplicative identity of Z mod 10. So that shows that I can't prove an analogous property for multiplication. Won't be true. However, the following fun fact is true. If phi from R to S is a ring homomorphism, and is surjective, then phi of 1 of R will equal 1 of S, assuming both rings have unity and are commutative. I don't think I need commutative that much, but I'm going to use the assumption that they have unity. Okay, so just make note that this example here is not a counterexample to Theorem 2 because this map was not surjective. That's what sort of saved this from having to send 1 to 1. So I realize as I write this, it must seem really counterintuitive, or at least not obvious, that surjectivity would have anything to do with sending the multiplicative identity of R to the multiplicative identity of S. Like, why is surjectivity the magic potion that makes that work? Well, we're going to find out here in just a minute. So here's the proof. So we're going to show that phi of 1 is a multiplicative identity sorry, my handwriting is terrible here, is a multiplicative identity for S. All right, well, how do we show something's a multiplicative identity? We show that multiplying it by anything in S doesn't change that thing. So here's how we do it. Suppose Y belongs to S. Then, and here's what I want to do. I want to show that phi of 1 times Y is equal to Y. And on the face of it, that seems like that would be hard to do. And I mean, as we now see, if I don't use the fact that phi is surjective, I won't be able to show that because that wasn't true up here in this example. But it turns out that knowing that phi is surjective is exactly what we need. Because since phi is surjective, there exists some x belonging to R such that phi of x is equal to y. Y has to be in the image of this map since the map is surjective. So then phi of 1 times y can be rewritten now as phi of 1 times phi of x. And that's the same as phi of 1 times x. And now you see how having surjectivity helps us, because now we can use the fact that we have a multiplicative identity in R and say, well, that's just phi of x, and phi of x is equal to y. And now we've done that for any y, an arbitrary y in S. So that means phi of 1R is a multiplicative identity of S. So that means phi of 1R has to be equal to 1S. Now you're probably asking, well, you said a multiplicative identity, like how do we know that S doesn't have several of those potentially? And the reason it doesn't is because we always know that a ring with unity has to have a unique multiplicative identity. The reason is if you were to pit these against each other, like let's say that these actually were different, but they're both multiplicative identities. If you were to multiply these two things together, well, because they're both multiplicative identities, the answer to that multiplication would simultaneously have to be this and this, and that means that these do have to be equal. So that's just a fun fact. You do know that phi of 1 is 1 if your map is surjective, of all things. Okay, here's one more fun one. This is actually important for later. Let's define the kernel of phi, where phi from R to S is a ring homomorphism. To be the set of all x in R such that phi of x equals 0. And I'm going to say 0 in S there just as a reminder that we're looking at all elements of the domain that go to the 0 in the codomain. All right, so it's the set of all inputs that go to 0. That's the kernel. Then, and here's the theorem statement, the kernel of phi is an ideal of R. Isn't that nice? So here's the proof. By the way, this is one of those good ones, and I hope that you've been doing this throughout the video anyway, but this is certainly a good occasion to stop the video and see if you can prove that the kernel of phi is an ideal, because you know how to prove something's an ideal, and the technique follows through beautifully here. But I'll go ahead and do the proof in case you're stuck or in case you want to check your work. All right, so to show that this is an ideal, first I need to establish it's non-empty. Well, by theorem 1 above, phi of 0 of R is equal to 0 of S. So that means 0 of R belongs to the kernel. So at least I know my kernel is a non-empty set, and it's a subset of R because we've defined it to be a subset of R. All right, so now we need to show it's closed under subtraction. We're going to use the two-step test where we prove it's closed under subtraction and absorbs multiplication. So to show the kernel is closed under subtraction, let's assume x1 and x2 both belong to the kernel. Well then, I want to show that the difference of those also belongs to the kernel. And how do I check that something belongs to the kernel? Well, I map it through and see if I get 0. So we have phi of x1 minus x2. Well, that's equal to phi of x1 plus the opposite of x2. And one thing that we haven't proven in this video, but you can prove, I'm going to leave this as something for you to do. So this part just follows from the fact that phi preserves addition. We know that already. But the next step is actually a result of phi preserving addition. The fact that I can take that negative sign or that opposite sign and pull it out. Okay, so this part needs a proof. Work on that. See if you can do it. Okay, the proof strategy is quite similar to what we did in theorem 1. And then at this point, well, we know that x1 and x2 both belong to the kernel, so both of those are equal to 0 of s. And over here, I guess we have the opposite of 0s. Okay, but the opposite of 0s is just 0s. So this all comes out to 0s. So that means x1 minus x2 belongs to the kernel of phi. So kernel of phi is closed under subtraction. Oh, there we go. All right. So to show that kernel of phi absorbs multiplication, similar process. Let's assume x belongs to the kernel and R just belongs to our domain. Okay, we have to let R be anything in the domain to show that kernel absorbs multiplication. And then we will show that XR belongs to the kernel. All right, so to do that, again, we're going to map it through and see what happens. So we have phi of XR, and because phi preserves multiplication, that's equal to phi of X, phi of R. And I don't know what phi of R is because R could be just anything in the ring, but I certainly know what phi of X is. That's 0s times phi of R. And at this point, it doesn't matter what phi of R is. Anything times 0 is 0. So XR does belong to the kernel. Great. So the kernel is closed under subtraction and absorbs multiplication. Therefore, the kernel of phi is an ideal of R.